Hi, it's me again, Clara. How are you? Over the last few weeks, we have been talking about crystalline materials. Today, we will change the topic and introduce you to the disordered and more chaotic materials, the amorphous materials. A solid is amorphous when the molecules do not present long-range order and are randomly oriented in different directions and different conformations. In strict terms, amorphous materials are liquids with very high viscosity. And how do we distinguish them from crystalline solids? Amorphous materials lack diffraction peaks in XRPD analysis and also lack of melting endotherm in the DSC. Instead, it may exhibit an apparent second-order phase transition called glass transition. The glass transition is a property of the batch, and it shows the temperature at which the molecules in the solid acquire a certain level of mobility. Above this temperature, the rearrangement of the molecules to produce crystalline solids is thermodynamically favorable. Like other solid forms, amorphous material will exhibit different physical and, potentially, chemical properties. In general, amorphous materials tend to exhibit higher solubility, which can be used to improve bioavailability and performance of our drug candidates. On the other hand, they also tend to be more hygroscopic than crystalline materials, and they can absorb significant amounts of water. Amorphous materials also exhibit different mechanical properties because of the different number and type of intermolecular interactions. In a way, we can think about amorphous form as the least stable form of a compound, and therefore it will have a tendency to change into the most stable form. Because of this, the amorphous form must be fully understood, and if chosen for progression, they must be stabilized to reduce risk of changes during development, storage, and manufacturing. We hope you find this new section of Solid State Foundations insightful. See you next month!